Next is predefined variables. So, here you can see that dim3 that we have already discussed, dim3 is a vector type. Apart from this vector type, there are some predefined variables just like grid dim, block IDX and third IDX. Grid dim basically gives the information about the dimension of the grids, which provides a total number of blocks in a grid, blocks that are arranged in x direction, y direction and z direction. Similarly, block dim, it gives the information about the blocks, dimension of the block. It indicates the total number of threads available in a block in each direction. So, block dim dot x, block dim dot y, block dim dot z indicate the number of threads in each direction. So, apart from this dimension, there are two more predefined variables, block IDX and thread IDX. So, since the blocks are arranged in a grid are maybe 2 dimension and maybe in 3 dimension. So, each block must have their unique ID, unique value based on its position in the grid. So, block IDX dot x, block IDX dot y and block IDX dot z indicates a block position in the grid. Similarly, if I talk about the threads in a block, these threads can also be arranged in a 1 dimension, 2 dimension and 3 dimension. So, that means one position is associated with each thread. To identify the position of each thread, so we have to use thread IDX dot x, thread IDX dot y and thread IDX dot z, which is basically indicating the position of the thread in the block. Now, I will discuss about how to invoke the kernel which we have declared in a CUDA program. The first step, we have already discussed in a CUDA program execution flow. First of all, we have to declare the kernel and then that kernel will be launched for the execution. So, there are two programs I have taken for explanation. Now, in the first program you can see that I have used the keyword that is global. Whenever I am using this global keyword and the function I have declared here is, that means that this is a function, this is known as kernel and it will be launched on the GPU, means it must be executed by the GPU. Apart from that, I have used a grid dim, you can see dim3 grid dim, dim3 and block dim. So, I have going to specify some number of blocks and number of threads in x, y, z directions. Last, you can see how this kernel, whatever the kernel I have written, how this kernel should be launched so that it can execute on the available GPU. So, you can see this kernel, this is a name, whatever the name I have used to define my kernel, the same name I will use here, and after that I will use triple brackets. Within that triple brackets, I am going to pass few parameters, grid dim and block dim, and after that we have to pass some inputs, because while defining this kernel I have not defined any parameters there, input parameters, or you can say input attributes I have not mentioned here. So, I am not passing anything here. So, what are the number of blocks and what are the number of threads in a block will be launched provided to the kernel, the kernel will be launched with the same configuration on the available SM. Suppose here I am using the one block and I am saying that only one thread. So, one block and one thread will be launched on the GPU. If I change this to 2 blocks, then 2 blocks will be launched and each block has only one thread, and so on. Now, I come to the second program, second kernel. Here I have just minute changes I had did. I just changed the kernel name here, and I am just providing the inputs and output and its size. 3 parameters I am providing to this kernel. These two are same as it is, which I have used for the first program. And now, just compare this launch function. So, instead of kernel, because I have it is a my kernel name. So, it is I have wrongly written kernel only. So, you have to use my kernel, K should be capital here. So, when I am launching this kernel, I am just passing the grid dim and block dim. So, in a previous case, I have not provided here any input to my kernel, but here when I declared my kernel, I declared the kernel with some parameters to be passed to this kernel. So, same parameter should be passed to this kernel when we launch this kernel in the program, otherwise it will throw some error. Apart from this two parameter grid dim and block dim, there are other parameters which can be specified when launching the CUDA kernel using the triple angle bracket. So, you can see here in this block I have mentioned that you can specify the shared memory size and stream. So, stream is right now I am not considering, it is out of scope for this course, but shared memory size you can think it of. So, you are defining how many bytes should be used within each block when it is launched on a SM. Next is a host and device memory functions. I will discuss these functions in detail, but for understanding purpose I have just given you some comparison. Just like in a standard C, there is a malloc function which is used to allocate the memory space on the system memory, means CPU's memory. And similarly, there is a CUDA malloc. CUDA has a function like CUDA malloc. This function is used to allocate the GPU's memory. Memcopy, this memcopy command is used to copy the data from one destination, source to destination. Similarly, CUDA memcopy function is used to copy the data from source to destination. Same functionality is memset, the same function we are using, and similarly there is another function is free the space of memory and CUDA memory. Now, I will discuss about the atomic function. Atomic functions are particularly useful when dealing with the global and shared memory, and especially to avoid the race condition. When multiple threads needs to update the same memory locations concurrently. These functions ensure that the only one thread at a time can modify a particular memory location effectively, and it is serializing the operation on that particular memory access. Meaning is that suppose there is a one memory location, I will say that memory location is A, B, 1, 2, some physical memory location it is, and multiple threads T0, T1, T2 is trying to access this memory location, but atomic function will say that at a particular time only this is blocked by the T0. When T0 will release, only then it will be blocked by the T1. So, that means number blocks are at a time is present to access this memory location. But atomic function, rather than accessing this location concurrently, so it is time division manner, the threads will access this memory location. So, that is the serialization effect. So, means at one clock cycle T0 thread T0 will access, in next clock cycle the thread 1 will access, and next clock cycle thread 2 will access. So, this is a serialization effect it will provide to avoid the race condition when we are using the atomic function. So, broadly atomic functions can be divided into two groups, bitwise atomic function and arithmetic atomic function. So, apart from that, I have provided the complete list of atomic functions which is supported by the CUDA programming model. So, developer can explore this atomic functions as per their requirement in their application. Next one is the synchronization function. There are several synchronization functions are required for the thread management, because threads are being launched in at various level, just like at warp level, at block level, at a entire GPU level. So, synchronization is required at different level of execution, right. So, in a simply say, the CUDA provides the synchronization at 3 levels. First one is the thread level, block level and device level. If you want the block level synchronization, then the synchronization function is _ sync thread. If you are using this synchronization function, so it is going to provide you the block level synchronization, and it will synchronize all the threads within a particular block. It ensures that all the threads reach the synchronization point before any thread in a block can proceed further. Next synchronization function is a warp _ sync warp function. It provides a warp level synchronization. As you know that in each warp there is a 32 threads. So, basically this synchronization function synchronizes all the threads within a warp. Next one is the CUDA device synchronize function. This provides the device level synchronization. It ensures that all the device side activities are finished before continuing on the host side. So, it is trying to maintain that device side all the activities must be synchronized before proceeding for the host side. Next kind of synchronization is a bit different of these three, that is a event based synchronization. So, whenever you apply this synchronization, so basically what happens, unless the particular event is occurred, all threads will not be synchronized. When that particular event will occur, all the threads reach to a certain point, after that particular event will occur, and then they can proceed for the next operation. So, now I am just comparing the atomic versus synchronization function. So, before that I will just give you a analogical example of atomic and synchronization, so that you can understand in a layman way. Suppose in a one office is there are multiple groups, or you can say multiple teams are working, but there is only one meeting room is available. So, that meeting room can be occupied by any of the team. Suppose in the same floor that team 1 is there, team 2 is there, team 3 is there, team 4 is there, and my meeting room is only one room. At a time any one of these 4 teams can be there. Suppose if in case of atomic, if room is occupied by T1 team, So, other two team T2, T3 and T4 cannot use that particular meeting room until unless it is free by the team 1. So, when team 1 is say that okay, my I have completed my meeting, so this is free and other team can take it. So, next team, any of it, out of 3 any of it who is available, he can occupy that meeting room. That is the activity of synchronization. Sorry, this is the activity of atomic operation. But then what is synchronization? Suppose one meeting room is available and all 4 teams wants to occupy this meeting room and all reach to the point and they ask to the administrator, I want to use this particular room, and then the caretaker or manager of that particular room will ask you whether team 1 all your members are present. Team 1 say no, only other members are, I am waiting for the members to come, and then if it will ask to team 2 or all your members are present, it will say no, my members are not present, and team 3 say yes, all my members are present and we are ready to occupy the room, and then manager will allocate this room to T3, because it is ensuring that all has reached to a certain point before proceeding further. So, that is the job of synchronization. So, you can by this analogy you can identify how the atomic operation works and how synchronization works in a various scenarios. Now, NVIDIA programming model provides several device query function. This device query function is quite useful, and using this device query functions and by passing some attributes, I can get the information about the underlying GPU, and you no need to study more about their microarchitecture and specification and all. By using this device query functions in your program, you simply write a one program based using this device query functions, and by passing some attributes, the information you want in that function, you can get the entire information related to that particular device. So, just I take an example here. So, the function is CU device get attribute, this is a function, and I want it and I want to get the information about this number of threads per block, maximum number of threads per block that particular device supports. This is an attribute I am passing. My function is CUDA device get attribute. So, it will return the maximum number of threads per block supported by that particular GPU. Similarly, you can see the function is same here, and now I want the information about the CUDA device attribute multi-processor count. How many multi-processors are available in my underlying GPU. So, by passing this function and by using this attribute, it will return you how many SMs are present. Suppose if the underlying GPU has 80 SMs, it will give you 80 SMs. It has a 108 SM, it will give you return the value 108 SMs, and so on. So, this is the reason I am just given you the list of some device query functions. So, developers can use these device query functions to get the more information about the underlying GPUs. Next one is the error handling functions. So, CUDA supports several error handling functions, and this error handling functions are quite useful for the application developer. By passing this error handling codes in your program, developer can identify the what is the exact cause of the problem. Basically, it can debug the problem easily by passing this CUDA error codes in their application. So, just like I just give an example of the first case CUDA error memory allocation. If any error is happening, if you have not passed, but any error is happening again and again, memory insufficient or memory related error is coming, by passing this kind of CUDA error code in your program, and it can indicate that if any error related to the memory allocation, it will tell you that memory allocation has failed, because of that your application is not going to execute. Thing is that the program has compiled, but when you are executing, the program is not getting successfully getting execute. Similarly, if you talk about this CUDA error launch failure, program has compiled successfully, but when you are trying to launch the CUDA kernel, it is getting failed. So, where it is getting failed, how it is getting failed. So, this kind of function, it can tell you that kernel has launched, not launched. So, I have provided some list of error handling functions. So, developers or learners can use this error handling functions in their code to know more about this functionality of this error handling functions. Now, there are the device specific flags and the optimization flags. So, suppose you are going to compile your application and you want to get the more information about your program or device code, so that you could debug the problem. So, you have to pass the -g, which is a debug mode, you can say. Apart from that, there is another flag, maximum register count. When you are passing this in your compilation, so you are indicating the compiler that limit the number of registers per thread to a specified number. So, per thread only launch 4 register or 8 register, whatever the number you will specify, that particular number of registers will be allocated to per thread. The third one is use fast math, device specific flag. So, whenever you use this flag, math related flag, it enables the fast math optimization. But when we are applying this fast math optimization, definitely it is going to reduce your precision. Now, I will discuss about the optimization flag. So, suppose you wanted to optimize your code for the underlying GPU. So, there are some options are available, O0, O1, O2 and O3, these are the options which specify the level of optimization you are expecting. So, O3 is the highest level of optimization. So, when you want to apply this optimization on the GPU, so how to pass this option? So, you have to pass this option with --x ptx as -option. This passes the option to the ptx assembler. Because CUDA supports the ptx assembler, so it can identify that the developer want the applications to be optimized for the underlying GPU. So, optimized assembler instructions will be come into the action, will be added in your program. After that, there is another one is fmat. Basically, you can enable and disable the fuse, multiply, add operations by making it true and false. While developing the application, you can develop some functions by using the fmat functions, and to enable that it should be performed by the fmat unit. So, then you have to pass this flags. So, there is some warning I have mentioned here. So, suppose you are compiling your file like this, nvcc-o file name with .cu and output file. So, in this case you have applied the highest level of optimization. You want that your code must be optimized with the highest level of optimization. But thing is that this optimization is going to optimize the code only for the host, not for the GPU. And if you want that your code must be optimized for the GPU, then this is the correct way to pass. So, hyphen hyphen xptx hyphen os, you have to pass this, because CUDA is based on the PTX assembler. In next topic, I will discuss about the NVIDIA GPU memory organization and various memory optimization techniques. Thank you.